Good evening, everyone. I am Barry Halverson, co-chair of the Lake Lawrence Lake Management District and Washington State Lake Management District Coordinator. This presentation is targeted to provide information on products that are intended to sequester or mitigate the harmful algal blooms or cyanobacteria problems many of us are experiencing in our lakes. Here are a few rules that we'll be following. Our presentation tonight will be by Pat Randall, West Sales and Technical Support for hepure. Pat will be providing a presentation on Zero Valent Iron. Paul, you should be able to share your screen now. Thank you for coming and addressing our many interested lake managers.
Basically, this is showing the different types of iron and the reactivities. On the far left, you can see where it says 10 micron. I put that in because there's a lot of interest for 10 micron. And what happens is it's very highly reactive, but does not last very long. So on the left side shows the reactivity. On the bottom scale, it shows the longevity, the time in seconds during this experiment. On the very bottom, you see the coarse iron, and you might see that it's not very reactive, but it will continue for a long, long time. 20 years plus is what we typically use for that. In the middle, the kind of orangish line would be our Ferox flow. It would be the 125 micron. It has higher reactivity. We'll lose that reactivity over, several years, and then eventually settle down, below Ferox PRB. But that may be about more like, we use about 10 years for that to happen. And then, or more than 10 years. And then the blue line up there is Ferox target, very reactive. And you can see that the reactivity falls off pretty quickly, but it does level off at about the same reactivity as the others. And we put that like up to 10 years, kind of depending on the environment that it's in. Make sure we're all talking about the same thing. Oxidation is the loss of electrons. And so zero valent iron is oxidized and it loses electrons. Fortunately, phosphate, which is already oxidized at +5, it really wants 5 electrons. And so the two will get together and form an iron phosphate stable, non-soluble precipitate. Like I say, you would think reduction would mean you're losing something, but you're actually not. The reduction is actually the acceptance of the electrons, and that's what's happening with phosphate. So phosphate's being fully oxidized must be reduced. It must accept electrons to become a non-soluble form. So the ZVI and the phosphate react together and form a very strong bond and form this ferric phosphate and ferrous phosphate. These are very stable. Unless you put them in like an acid solution or something in the chemistry happens pretty significantly, they would not be expected to come back into solution. The phosphate will stay in the precipitate. In this case here, it would stay in your lake bottom. So there's been some discussion of how ZVI can work without oxygen present, and it does. It reacts with water, it reacts with other chemistries to lose its electrons and then combine with the phosphate. If you do have oxidants present, it is more reactive, but it doesn't mean that it will not react if there's no oxygen present, although there will be oxygen present in the lake. The next slide, I believe, will show kind of the difference in this. What this slide is showing is if you look at the red line above the black line, that's the addition of hydrogen peroxide, which is trying to mimic having more oxygen. And like I say, the reactivity or the removal rates does increase slightly, but not a lot. Now, it will depend on how much oxygen or how much hydrogen peroxide you add. If you look at the other two, we're adding a stronger oxidant and we do get a stronger reaction. So once again, having an oxidant or having oxygen present is a plus, but it is not absolutely necessary. And that's what this is kind of showing you. So in this slide, we're looking at 4 ways that ZVI is used in treating phosphates at lakes. Up there by the tractor, you can see there's a little brown spot. That's a barrier, and we've had some people that when they have a creek or something like that come in, they build like a structure for the ZVI to be placed into, and that water has to pass through that, and it removes phosphates and nitrates and some other chemicals before it gets into the lake. The most common, and what you've probably a lot of discussion you've had, is just to the center of the slide where it says surface through the water column. This is where you broadcast the ZVI, either dry or in a slurry. It really doesn't matter, whatever method is easiest, over the top of the lake, and the ZVI flows down to the bottom of the lake. As it does, it reacts with the phosphate in the lake water, removing it. I'm going to tell you right now, to my surprise, it's been very, very effective for the little bit that's put in. It surprises me. And the last one, if you look at the very bottom, there's that brown spot down there. So we've had cases where there's groundwater percolating in from the bottom of the lake. I believe Stellacom was one, and they actually went into those areas and put Ferox PRB over the top of it. And the idea was, is as the water came up through the bottom of the sediment and then came up into the lake, it would pass through the PRB and the phosphate would be converted and trapped. And then also, if there's enough conditions, the sediment, the phosphate within the sediment can, depending on how it's bound up, also be released from the sediment. And the target that you've put over the surface of the lake, or if you put something over the bottom of the lake, then that helps prevent the re-release of phosphate from the sediment. So these are the 4 areas that we kind of look at, are looked at for treating phosphate in lakes. So there was some discussion going around about the effect of ZVI on DO and pH, and it does have an effect. And what we've seen is the effect is short term, that it will bring the DO down, it will raise the pH slightly. But as the aquifer absorbs this chemical change and more DO comes in, it basically recovers. We haven't had any reports of, any fish kills or any adverse effects from any of the lakes that it's been applied to. So, and typically in our applications, there is a small change, but there is a change. The next slide shows another part of the same site with this test, and it's a little bit less of an effect. And for your information, the dashed line there is the line at which the application took place. So you can see there was an effect on DO here and an effect on pH. But it's really going to depend on the chemistry, on how, and throughout the lake, it's going to be a lot of difference. So it's just ones I looked up where we've supported projects, lake projects, in the last few years. That's the end of this part of the presentation. We're going to go through the spreadsheet next, but I wanted to pause and see if there was any questions, and I can go back to a slide if need be, if somebody has a question, or maybe I can just answer it.
Go ahead, Janice.
You said something about you apply it and then they noticed that the DO, dissolved oxygen, came in. You said it will come in. How does dissolved oxygen come in?
Well, you're absorbing dissolved oxygen either from the water coming in from other sources like runoff or whatever, and a lot from the lake surface. So you're constantly getting more oxygen. And so that replenishes whatever oxygen is used up. Right now, your growth, your organic growth, is using a lot of that oxygen. And once again, for the longest time, it will reduce the oxygen, but as long as more oxygen is absorbed from the surface or other areas, you don't get the fish kills. When the algae is using more oxygen than what can come into the lake, that's when you get a fish kill. Does that answer your question?
This is Jeff. Could I just clarify the slides that showed the oxygen and the pH? Those were situations where you had injected iron into the groundwater in a well or something. Is that right?
Into groundwater, yes.
So I think that's quite different from the situation in a lake, because groundwater is not in communication with the atmosphere, whereas a lake is. And particularly if you apply iron at a time of the year when the lake is not stratified, you're going to have continuous interaction with the entire water column with the atmosphere. So I think those oxygen depletion concerns are less in a lake than they would be in groundwater.
Most likely, we do. Oh, go ahead. I'm sorry.
Well, I was just going to add on, is the same true for the pH? Because your slide showed the pH going from 7 up to 10 and being there for a couple of months.
Right, and Jeff's right. In the aquifers we're normally dealing with, what we're depending is there is a slight, at the top of the aquifer, there is a slight interaction with some air, but not much. Mostly what we're seeing is new water passing through that area in which the iron has been placed. And so it's more of a run-on type of situation than what it is absorption from the surface. And so basically that is why we typically don't see long-term effects, and we haven't really seen aquifers go fully anaerobic. Could you put enough iron in there to do that? Possibly. I don't know. That would be quite a bit of iron.
Yeah, but we're
Can
not.
you do that?
Excuse me. We're not talking aquifers here. We're talking lakes.
I know.
And that's what I want. I want to concentrate on lakes, not aquifers. I understand water comes in, it percolates up from the bottom from aquifers, but that really is going to just bring phosphorus into the lake, additional phosphorus. That's what we found with the springs that we have.
Okay.
So the idea is the problem that we have been told that we have with iron is that you put the iron down there in anoxic conditions, and the DO, dissolved oxygen, gets so low that the phosphorus releases from the iron particles. So I'd like you to address that part of it.
Well, all I can say is I'm not familiar with any chemistry in which that would happen.
Okay.
Like you say, once you have the phosphorus in the combined with iron, they're sharing the electrons. You have to have some sort of force break it apart. Typically, that force would be, in a chemical situation, would be a strong acid. If you don't have any oxygen, because the oxygen, if you look at the iron phosphate bond, there's no oxygen involved in that. There's no oxygen involved in any of the process. So I'm not quite sure where that came from, but I don't, we don't see it. When we do barriers, we have, well, I guess we don't go to zero oxygen. So that wouldn't be, all I can say is I'm not familiar with any chemistry in which that would be true.
Okay. Thank you.
Could I add one thing about the pH question?
Sure.
So in most lakes, pH is buffered because you have carbon dioxide in equilibrium with the atmosphere. And we don't have to go through all the chemistry right now, but that's a natural buffer which really prevents wide swings in pH unless you have extreme events, which I don't think is applicable to this situation. So again, a lake is a large volume of water, and the volume of iron being added is small. That's really different from injecting iron into groundwater, which is a slow turnover system with a smaller volume of water. So I guess I would just echo Pat that there isn't any situation I've ever read about where applying iron caused a shift in the pH that was significant.
Okay. And Jeff, that also equates to DO.
Correct.
Okay. And the reason I asked the question is because we've had 6 other presentations prior to this, and a lot of them have talked about iron and DO controversies between lack of dissolved oxygen impacts, how the iron's going to work to take phosphorus out of the water column, and if you don't have enough DO or the dissolved oxygen content goes anoxic, then the phosphorus is released from the iron and then comes up into the water column and causes an algae bloom. And what I'm hearing you say is that there's no science that would support that.
I would say that phosphorus does get released from sediment. There's no question about that. It will accumulate in the hypolimnion if you don't have enough iron in the system.
Right.
In which case, then you can have a bloom if that water column turns over and that iron and that phosphorus goes up into the photic zone. But it's not clear to me that the phosphorus that's being released is coming from iron dissolution.
Okay.
It's coming from organic matter decomposing and having not enough iron to sequester it.
Okay.
Any other question? I'll go to the spreadsheet if there's no other questions.
Well, that'd be a good place to probably get questions, Pat.
Talked about the impact of dissolved oxygen. And I think that compared to other demands on oxygen, like the decomposition of organic matter, iron is negligible. Particularly if it's applied early in the season, which would make sense in terms of controlling an algal bloom. Then you're applying it at a time of year when the water column is oxygenated all the way to the bottom. It doesn't have any significant effect on pH in a lake system. I would say 2 things. One, we've done that at Lake Steilacoom, and it was very successful. After we used a finer particulate size, which, as Pat said, is very reactive, and he showed reaction times on the order of hours. So at Lake Steilacoom, after we applied it and then we measured SRP in the water column, it was below detection. So based on that study, I would say that it is a successful approach. Applying it to sediment, then you're putting a blanket on the bottom. The observation in nature is that if the ratio of iron to phosphorus is above about 10, then you don't have significant phosphorus release from the bottom. So that's just nature talking. In terms of using it on the bottom, and enhancing what's already there, I'm not aware of a lot of studies where they've actually measured before and after, so I can't give you any citations. I would just say that my understanding of how the system works is that if you have enough iron in the system, it does its job. And then, for example, at Spanaway Lake, which is a lake that has naturally high iron in the sediment and is above that 15-to-1 ratio, when phosphorus comes out, it binds with iron that's dissolved in the water and then reprecipitates. And the evidence for this is that there is high iron in the water in the hypolimnion at Spanaway Lake, but SRP is below 10 ppb in everybody's analyses. And the only way I can explain that is that the iron is binding the phosphorus while it's still in the hypolimnion. It's been released from the sediment, but it's never made it into the water column in a way that algae can use it. Longevity, I don't have any data on that. Pat has some results of studies that show how long it remains effective in his applications. So maybe somebody else could provide more data on that.
Well, we discussed it in the slides.
Right.
Like I say, it's in saturated conditions, either in an aquifer or in stream beds. We have people do treatment of like arsenic and other metals in mine waste lakes, and we've never seen anything less than 10 years. So it's very, very has a lot of longevity. Now, in the case of broadcasting it, obviously, it's only going to remove from the lake waters as it's filtering down through. But once it gets into the sediments, it's going to be there active for a long time.
So expected cyanobacteria reduction, it's been successful at Lake Steilacoom. So if you can bring SRP down in the 10 pp and below range, then it should be successful at preventing cyanobacteria blooms. That's no different than any other product. If you can successfully remove SRP, you've taken away the food.
Okay, so on this one in particular, cost and logistics, 166 pounds of ZVI per acre. I thought we measured ratio of product to pounds of phosphorus in pounds of product, not per acre. So I didn't understand this. I asked the question in a question back to Pat after I received the slide presentation. So can someone elaborate on that?
Well, I'll take a stab at it here. So I think this is the broadcast rate, and typically in all of our projects, the amount of iron needed to react with the chemical in question is small. And that's because the stoichiometric ratio, you don't have a lot of contaminant. And if it was in a beaker and you stirred it up, it would make contact. So basically, what you need to do is put enough on to make contact to get the contaminant, in contact with the ZVI, and that's the driving force behind how much you put in. Okay. So stoichiometry is secondary.
Kyle, do you want to talk about how we calculated this? Because I think there's a way we got to this pounds per acre.
Yeah, I'd like to go over it with you again. It was quite the calculation, but we came up with 166 pounds to increase the ratio on that bottom sediment, because that's what Lake Lawrence has the issue with.
Okay.
And that would also include, obviously that first application would be stripping the water column. Mm-hmm. Anything that wasn't used up during that process would sit at the bottom and sequester anything coming out of the sediment.
Okay. So the 166 pounds per acre was geared toward the 7,225 pounds of phosphorus in Lake Lawrence.
It was based on the data that you shared with me about the iron phosphorus content of the sediment and the iron content of the sediment.
Okay, good.
And the goal was to enhance the iron to get to this 15-to-1 ratio,
Okay.
but not necessarily in one fell swoop, because every time you add it, you get a free benefit basically of stripping the water column.
Right. So that 166 pounds of ZVI per acre may not get us to the total amount of iron that we need in the bottom sediment.
Correct.
Okay. Got it.
I would say that that's an unknown number.
Correct.
Nature says 10, but we don't really know that number precisely.
Okay. And for both types of product, a slurry is the recommended application method?
We've done both. We've broadcast the heavier stuff, and we've slurried the smaller micron material.
Okay.
We could slurry both.
Okay. Water testing requirements. I just want to clarify there is no mandatory water testing requirements in the APAM for application of ZVI, correct?
Correct.
Okay, so the recommendations in the documents we received were recommendations in order to monitor progress or lack thereof and total phosphorus after application.
Correct.
Okay. So did you do SRP, DO, pH, etc. on Stellicum before and after?
We didn't do DO or pH, but we did TP and SRP.
Okay. And could you send me the results of those tests?
Yep.
Okay, I'd appreciate it. Okay.
I guess I just want to say, I think, Jeff, you had talked to us about iron usage earlier this year. Is that true? Like a month
Yes,
ago?
I did. Yes.
Okay. And you did a great job. I was sold on iron. And then, like Barry said, the rest of the people came in and said,
I mean, I can guess what she was going to ask.
Go ahead, give it a shot, Jeff.
Okay, so I talked about, why I thought iron would and wouldn't work in certain circumstances, and then I think she was going to say that you've heard other presentations that cast serious doubt on the ability of ZVI to work under low oxygen conditions.
Correct.
And I think ZVI has not been widely used in lakes because of that concern, but there's a real lack of data that shows that that's actually a problem. And in cases where I think caution is necessary would be places where you know that the bottom waters are strongly reducing, like you have hydrogen sulfide production, which would show up in the smell. And it doesn't seem to me that was part of the evidence that was presented for Lake Lawrence. So what we do know is that, dozens of studies of natural lakes show that when your iron to phosphorus ratio is high, you don't have a problem with phosphorus release. And that was not screened only to lakes that had oxygenated bottom waters. That was just a study of a lot of different lakes around the world. So I think that supports the idea that fears about oxygen, low levels of oxygen, are overstated. And I would reiterate that low oxygen is not the same as strongly reducing. Low oxygen is not a concern. Even no oxygen is not a concern unless you get to the point where you're starting to get hydrogen sulfide and signs that you have become far more reducing than just no dissolved oxygen. So I don't know whether sort of
Okay.
data I can share, but that's what I'm aware of.
Okay. All right. Thank you, Jeff. I appreciate it. Here is our contact information at Lake Lawrence. I'll give you a second. If you liked this presentation, please give us a thumbs up. Here are a few other videos you might find educational and interesting. And hit the subscribe button in the lower right corner to get automatic notifications when the new videos are posted to this YouTube channel. Hope you all have a great day.